Hi everyone, this is Alireza Khadem, a PhD student from the University of Michigan, advised by Professor Das. Today I'm going to present vector processing for mobile devices, benchmark and analysis. To understand the concept of this presentation, first we provide the background of the vector processing and compare its benefits with domain-specific accelerators. We start with a simple example of vector add. The left code snippet shows the scalar implementation while the right code is the vectorized version. Vector processing uses a single instruction to operate on multiple data. Therefore, vector processing reduces the number of loop iterations from 128 to 32 in this example. Fewer instructions improve the performance. A vector instruction is fetched and decoded once in the front-end modules of the CPU, while it processes multiple data in a back-end vector pipeline. Therefore, vector processing reduces dynamic energy consumed by the front-end modules and the static energy of whole CPU because of a shorter execution time. Vector processing is specifically important for the resource-constrained mobile devices to enhance the compute throughput and battery life. Vector processing was first deployed in the supercomputers for high-performance computing workloads in 1970s and 1980s. Due to the high data-level parallelism of multimedia workloads, multimedia instruction set architecture extension were introduced in 1990s. Vector processing evolved by supporting various data types, wider registers, more registers, and sophisticated instructions for a variety of application domains. ARM introduced Neon technology in 2005, which is the dominant vector extension used in the state-of-the-art mobile processors. Today, vector pipelines are prevalent in all processors, from supercomputers to embedded microcontrollers. In addition to the vector pipelines that are tightly integrated to the CPU cores, today's mobile devices contain a variety of domain-specific accelerators, such as GPU and DSP. A closer look at the evaluated mobile SoC shows that the Hexagon DSP is also a vector processor with 4 1024-bit vector pipelines. However, programming DSP is very complicated and requires the knowledge of Hexagon vector extension APIs, interface description languages, and sophisticated makefiles. In addition, DSP vector extension only supports fixed-point arithmetic, while ARM Neon supports half and single precision floating point operations. Another problem with the domain-specific accelerators is that they are loosely decoupled from the CPU cores. We observe that only the kernel launch overhead of GPU is around 2 times more than the total ARM Neon execution time in the evaluated data parallel workloads. Due to the high throughput, hard programmability, and high kernel launch overhead, GPU and DSP are only efficient for the coarse-grained offload of large problem sizes. On the other hand, vector processing is suitable for the fine-grained interleaving of scalar and data parallel code, while it supports a variety of instruction types and operation precisions. While vector processing is critical for mobile devices due to the high performance and energy efficiency, this Venn diagram shows that none of the prior benchmark suites are designed for studying the strengths and weaknesses of vector processing for mobile devices using multiple application domains. Therefore, we present SWAN, a vector processing benchmark suite for mobile devices. Using SWAN, we study the performance, power, energy, and scalability of vectorized workloads and provide interesting insights for application developers, vector ISA designers, compiler developers, and computer architects. Now that we know about the benefits of vector processing for mobile devices, let's discuss the scope and workloads of the SWAN benchmark suite. To create the SWAN benchmark suite, we studied the source code of 4 frequently used mobile applications: Android, which is an operating system for mobile devices, a web browser Chromium, an audio and video messaging application or WebRTC, and PDFium, which is a PDF rendering engine. To enhance the coverage of our benchmark suite, we pick 12 libraries that are commonly used in these 4 mobile applications from multiple domains. Finally, we profile Google Chrome while browsing top visited websites and pick 59 time-consuming data parallel kernels. Swan Benchmark Suite is maintained online on GitHub. You can access both scalar and vectorized versions of data parallel kernels, compilation infrastructure with multiple kernel execution modes, performance and power profiling utilities, and a fake ARM Neon library with wider vectors from the GitHub. Now we briefly explain the application of these libraries in the context of the web browsers. A web page is consisted of various web contents that are downloaded over an encrypted communication with the web servers using Boring SSL library. An image is decompressed, decoded, enhanced, converted to other color spaces, and rasterized on the display using the kernels of 5 libraries in the Swan benchmark suite. Swan includes 3 libraries to decode, synthesize, and analyze an audio sample. Videos are decoded using libvpx, and machine learning web applications based on JavaScript are executed using Zenpack. In addition, ARM-optimized routines contains string utility primitives such as memcopy and memset, which is used across the code base of all applications. Now let's explain our evaluation environment and input data sizes. We cross-compiled the Scalar and Neon implementation using Android NDK. In addition, we compiled the Scalar baseline with LLVM's auto-vectorization to evaluate compiler vectorization benefits and limitations. Our mobile device contains a Qualcomm Snapdragon 855 SoC. We evaluate the high-performance ARM Cortex-A76 Prime core, which is a 4-way superscalar and auto-order core with 2 128-bit vector pipelines. We use SimplePerf to profile the performance counters of the mobile device. Finally, we feed our workloads with HD images, 1 second of a standard voice, 128 kilobyte of raw data, and 156 convolutional layers. Now it's time to evaluate Swan workloads on the mobile device. We start by showing the diversity of Swan workloads by studying the instruction distribution of workloads. Swan contains 3 libraries with a high fraction of scalar instructions and 3 libraries with a high fraction of memory accesses. 2 libraries use accelerated crypto instructions for cryptography and data compression workloads, and 4 libraries contain floating point arithmetic for audio processing and machine learning workloads. Therefore, Swan contains workloads with various operation precisions and instruction types. Next, we discuss how vector processing reduces the number of instructions. This chart shows our Neon's dynamic instruction reduction compared to the scalar baseline. Vector processing reduces the number of dynamic instructions from 2.7 times in PFFFT and libopus to 10.9 times in the zlib library. Cryptography and data compression libraries achieve the highest dynamic instruction reductions. This is because these libraries use accelerated instructions which encode multiple bitwise operations in a single instruction. Next, image processing, video processing, and string utility libraries significantly reduce the instructions. These libraries process 8-bit data. With a constant width of 128-bit, vector registers efficiently encode many low-precision data elements that highly reduce the number of instructions. On the other hand, vector processing cannot efficiently reduce the instructions in 3 application domains. Despite the previous libraries, graphics, machine learning, and audio processing libraries operate on high-precision 32-bit data elements, which reduces the number of operations encoded by a vector instruction. Now that we know what affects Neon's ability to reduce the number of instructions, let's see how Neon enhances the performance. We compare the performance improvement of vector processing in this chart. Compared to the scalar implementation, Neon reduces the execution time from 1.8 times for the web audio library to 11.6 times in the Boring SSL library. Comparing the performance improvement and instruction reduction shows that these two parameters are highly correlated. Image processing libraries, however, does not follow the same trend. This is because these libraries operate on large working sets, which substantially increases the miss per kilo instruction or MPKI of the first level of the cache. We observe that explicitly vectorizing kernels using ARM Neon extension achieves up to 11.6 times speedup. This is a common belief that compiler auto-vectorization requires less effort from programmers while achieving acceptable performance speedups. Let's investigate this claim. This chart compares the performance of auto-vectorized scalar kernels with explicitly vectorized ARM Neon kernels. Neon, on average, outperforms auto-vectorization by 3.7 times. We observe that auto-vectorization only improves the performance of 23 scalar kernels. In other words, compiler vectorization fails in 36 scalar kernels of Swan benchmark suite. To understand the reasons of compiler vectorization failure, we explain LLVM's auto-vectorizer. In the first step, compiler evaluates the legality of the vectorization. Legality is proved with two conditions. First, compiler assures the correctness of vectorization, meaning that the output of the vectorized code must be exactly same as the output of the scalar code. For example, if a loop is not countable, or it is a for loop with a break condition or a while loop with an undetermined trip count, compiler is unable to correctly vectorize it. Vectorizing an uncountable loop, which occurs in 8 data parallel kernels of the Swan benchmark suite, requires complicated loop transformations, which is outside the power of the LLVM's auto-vectorizer. The second condition for legality is the safety of memory accesses. Compiler only vectorizes the loops with the memory accesses to the legal memory addresses. For example, lookup tables are frequently used in the scalar code to convert multiple arithmetic operations to a single lookup table access. However, lookup table accesses fail LLVM's auto-vectorization in 8 kernels of Swan benchmark suite. This is because lookup tables are suitable for auto-order superscalar execution, where instruction-level parallelism is critical. Most of the packs in the instruction sets, including ARM Neon, does not support indirect memory accesses. In the next step of the vectorization, LLVM analyzes the benefits and costs of the vectorization using a heuristic cost model. However, this cost model is not accurate because it does not have access to runtime information such as loop trip counts and control flow behaviors such as branch conditions. In addition, compiler does not have enough information about the instruction throughput and latency of the target machine. Therefore, an inaccurate cost model fails auto-vectorization in 12 kernels of the Swan benchmark suite. In summary, we showed that despite the common belief, auto-vectorizing the legacy scalar code without any efforts from the programmers does not harness the power of vector processing for data parallel workloads. Now that we know about performance improvement, let's discuss the power and energy consumption. This chart shows that vector processing increases the power consumption of the SoC by up to 40% compared to the scalar baseline. This is because vector processing increases the rate of memory accesses, which subsequently increases the power consumption of memory subsystem. However, vector processing can reduce energy consumption by up to 10.4 times. Vector processing reduces both the dynamic and static energy consumption of the CPU cores thanks to fewer instructions and shorter execution time. So, if you are targeting the thermal design power or TDP of the chip, vector processing is not suitable for you to focus on. But if you are trying to increase the battery life of the mobile processors, you should exploit vector processing for any data parallel kernel. Next, we studied the bottlenecks of vector processing using Intel's top-down microarchitecture analysis. First, we observed that vector processing reduces the instruction per cycle or IPC of the data parallel kernels. Our profile result shows that vector processing is mainly bottlenecked by the backend stalls of the core. On average, 35% of the cycles are stalled by the backend stalls. Finally, we relate the backend stalls to the cache misses. We conclude that vector processing improves the computational power and increases the rate of the memory accesses. Therefore, it increases the pressure on the memory subsystem, which is the main bottleneck to achieve a high IPC. In the next section, we describe 4 computational patterns of vectorized kernels. These insights would be helpful for the design of vector instruction set architecture extensions. A strided memory access targets memory locations with a constant stride. For example, when accessing every other memory locations, the stride value is 2. Armnion provides memory accesses with the stride of 2 and 4, which are deployed in 2 and 10 kernels of Swan benchmark suite. Longer strides significantly simplify the vectorized kernels, yet they increase the hardware complexity too. Random memory accesses use a source vector register as the indices to the memory locations. This memory access pattern is primarily used for accessing lookup tables in 7 scalar kernels of the Swan benchmark suite. Since Armnion does not provide any instruction to support this access pattern, Neon implementations don't use lookup table accesses. Reduction is prevalent in many application domains. We observe that data parallel kernels vectorize reduction operations in 2 ways. 2 kernels of the Swan benchmark suite compute multiple reduction operations in parallel as the data elements of a vector register. However, inter-reduction parallelism requires interleaving input data for the vector memory accesses to load data in a vector register. Here, long-strided memory accesses could be helpful to load and interleave the input data elements. Alternatively, 3 kernels exploit the parallelism inside the reduction operation. On the other hand, intra-reduction parallelism requires an associative and commutative reduction function. Finally, we observe that matrix transposition is frequently used in data parallel mobile applications. Swan contains 4x4 and 8x8 matrix transposition primitives as a part of the PFFFT and libdpx libraries. Using these 2 primitives, one can transpose any arbitrary size matrices. Long-strided memory accesses could significantly simplify these matrix transposition primitives. Finally, we analyzed the scalability of vector processing in 2 separate experiments, wider vectors and more vector pipelines. Armnion provides 64 and 128-bit vectors. In the first experiment, we increased the width of vectors to up to 1024 bits. To exploit a higher degree of data level parallelism, 4 times wider vectors require 4 times wider vector register file and ALUs, but no changes in the front-end modules of the core is needed. The evaluated mobile processor provides 2 vector pipelines. In the second experiment, we increased the number of vector pipelines to 4, 6, and 8. 4 times more vector pipelines exploit 4 times more instruction level parallelism and require 4 times more vector register ports and ALUs. We develop a fake Armnion library that emulates 213 intrinsics for 5 wide register types and redevelop 8 sample kernels with diverse computational patterns using this library. We compile the kernels using LLVM and dump the dynamic instruction traces using a Dynameria client. Finally, we analyze these kernels using an in-house cycle-accurate ARM simulator. This chart shows the performance scalability with wider registers. We observe that the performance is highly scaled in 5 data parallel kernels and weakly scaled in these 2 kernels. This is because these kernels perform reduction operation. A wide vector register requires reducing many partial reduction results to a single final reduction output using many vector manipulation instructions, which limits the performance benefits. In 2 kernels, wider vectors achieve no performance benefits. This is because these kernels access multidimensional data structures from the memory, such as a 2D block of a 2D image. Multidimensional strided memory accesses require many vector manipulation instructions to pack partial memory accesses to a wide vector register, which limits the performance benefits. Next, we increase the number of vector pipelines from 2 to 4, 6, and 8 for a 4-way superscalar core. We observe that performance is not scaled on top of a 4-vector pipeline design. This is because insufficient instructions are issued to the vector pipelines from the front-end modules, which reduces the utilization of the vector pipelines. In the second experiment, we also increase the number of superscalar ways with the vector pipelines. We observe that performance is weakly scaled with more vector pipelines. This is because LLVM's instruction scheduler and register allocator reduces the instruction level parallelism in kernels with high register pressure. We conclude that increasing the number of vector pipelines also requires increasing the throughput of the front-end modules to enhance the utilization of vector pipelines. Finally, we compare a design with 4 times wider registers with another design with 4 times more pipelines. Using data level parallelism, wider vectors enhance performance by 2.4 times, while more vector pipelines exploit limited instruction level parallelism to improve performance by 1.6 times. Compared to more vector pipelines, wider vectors require higher vector register file area, less front-end modifications, and comparable vector ALU sizes. Wider vectors are bottlenecked by the lack of multidimensional memory accesses in the instruction set, while more vector pipelines are limited because of high register pressure. Finally, we conclude and give directions for the future work. We introduce SWAN, the first vector processing benchmark suite for mobile devices. We observe that vector processing reduces the dynamic instruction count, enhances the performance, and improves the energy consumption. Compiler autovectorizer fails in most of the kernels due to the complicated loop transformations and limited compile time information. We studied the performance scalability of wider vector registers and more vector pipelines. Wider vector registers achieve a stronger scalability but require larger vector register files. We plan to extend the SWAN benchmark suite by adding the RISC-V RVV and ARM-SV implementation of the current data parallel kernels, benchmarking the Android Java applications such as social media, calendar, email client, and navigation, and evaluating high-performance web applications such as web games. Thank you for your precious time. You can access SWAN benchmark suite on our GitHub repository.